Module 4X, Examples of Fourier Analysis. In this module, we are going to explore how Fourier analysis can help us understand signals, and why it is worthwhile investing so much effort understanding the Fourier transform. We will do this with 4 different examples. The first one is looking at musical instruments and understanding their spectra. The second one is to look at a very classic periodical phenomenon, namely the tides, and in a specific case, namely in Venice. Then we'll explain how MP3 compression works from a perceptual point of view. And last, we are going to look at a medical imaging application which is called magnetic resonance imaging. Let us look at the analysis of musical instruments. So we all know about pitch. What is the basic frequency, for example, of a singing voice or a particular instrument playing a note? So it is about frequency or cycles per second of the waveform. However, there is not only the basic frequency, there are also harmonics. So if the basic frequency is omega 0, you have 2 omega 0, 3 omega 0, 4 omega 0, etc. that appear also typically in the sound. And the shape of these harmonics, how big they are, actually gives the timbre of the instrument, the characteristic of a particular sound. So let's compare 3 particular instruments, a cello, a sax, and a violin, by looking at their Fourier spectra and understanding how the harmonics can look very different and give very different types of sounds. If you look at the waveform of a particular instrument, it is very hard to see how it's going to sound. And we know this from, for example, the waveform of a speech signal. It's very hard to understand speech by looking at the waveform of the signal. So here, the first case, we have a saxophone, and we see a few periods of the basic sound. That's the sound pressure that is generated by the saxophone playing. Let us play this instrument. Now let's look at a very different instrument, namely a violin. Again, we see a few periods of the sound that was recorded from a violin playing. It looks different, but we don't exactly know what is the difference going to be. So let's play this instrument. And let's look at the third instrument, a cello. The waveform looks different from the violin, so let us listen to it. Okay, so now we have heard 3 different sounds, and if we were to play them back to you, can you guess what instrument it is playing and what is the note that the instrument is playing? That depends on your training, and many people can do this very well, but we're going to see a mathematical method to do this, which is to take the Fourier transform, or the discrete Fourier transform in this case, of a few periods of this signal. The message is, of course, that in time domain it is not easy to understand the signal. In Fourier domain it will be much easier. So here we plot the magnitude of the discrete Fourier transform coefficients taken from a few periods of these various signals. And we plot them between 0 and 1.32 kilohertz. On top you see the sax. It has a few peaks, as you can see, at 220, 440, 660, etc. Then we have the violin. It has also a peak at 220, but a high peak at 880. And at the bottom, the cello has also a peak at 220, like the sax. It's a big one. Then at 440, and then it decays and goes back up at 1320. So you see the spectra look very different. And definitely the violin looks very different from the cello and the sax. To some extent, the saxophone and the cello have somewhat of a similar sound, a warm, basic sound, and the violin is, as you can see from the peak at 880, has a more high-frequency nature to it. So the note is each time played at 20 Hertz. The other peaks are what we call harmonics, And without using the Fourier transform, unless you're a trained musician, we might be lost. In sum, by looking at the Fourier spectrum, we can see that the fundamental note is the first peak in the spectrum. It's not necessarily the biggest peak, but it's the first one that appears. That's a note that is being played. The further peaks are the harmonics, and they are all multiples of the basic note. And the relative size of the harmonics gives the timbre or the characteristic of an instrument. And so here we see in a very simple example where the signal is periodic that the discrete Fourier transform is very helpful in understanding these musical sounds. The second example is the approximation of a periodic signal by using only a few coefficients of a Fourier transform, or in this case a discrete Fourier transform. Periodic phenomena are very widespread in nature for many reasons, and the one we're going to look at is the phenomenon of tides. This is a phenomenon that has been studied for centuries and has been used in Fourier analysis also at a very early time of Fourier analysis in the 19th century. Now, the idea of doing the approximation is a fundamental step that we will encounter again when we look at compression of signals. Here, really, the goal will be ultimately to do a prediction of tides, but the first step in prediction is to find a low-order model. So, what is the problem of tide prediction? Well, the tides are a phenomenon linked to the movement of the sun, of the moon, of the rotation of the earth, and so on. So all these things are periodic, but they are not all of the same period. So we have a phenomenon that is only to first order a simple periodic phenomenon. Now, tides are of course important because they can lead to some trouble, and here in Venice is a case in point. Every now and then the tides plus other natural phenomena lead to floods in Venice, and this is either for the fun of the tourists or for the annoyance of the people that try to make a living there. So can we try to predict when there will be flooding in Venice? And the first step is, as we mentioned, to approximate the tides. The data set we're going to look at is hourly measurements taken in the Grand Canal during the year 2011, so that's very recent data. And we can look, for example, here at 3 days of measurements, so that's 72 hours. You can see it's a smooth curve and it has a periodic feel to it, but it's not completely clear what the period is, what the components would be in a Fourier transform. So we shall take a Fourier transform of such a signal and then see how to approximate this periodic signal. So if we take 1 year of measurement and we take a Fourier transform, now the frequency is in 1/hours, we can see that there are a few peaks and then there is a lot of noise. The DFT magnitude is plotted on a log scale here. It's very important. So you take the DFT, you take the magnitude of its coefficients and then take the level in dB or in logarithm in base 10. Therefore, you can see all the components on a very short scale, and you can see there is, a peak at 0, then a peak moving to a couple of peaks moving towards 400, a couple of peaks around 700, and a lot of other information that we don't quite understand. So let's do now an approximation of this periodic signal, and we consider either 1 Fourier coefficient, 3, 5, or 11. So that's a very small number with respect to the potential number of Fourier coefficients needed to exactly represent the signal. And we're going to start with light gray approximation, which is 1 coefficient. So the 1 coefficient is the constant. So that's when you simply average out all the signal values and you get this sea level in centimeter approximation in gray, which is a constant. Not a very good approximation, just the average. The second one is the constant plus cosine wave. So that's 3 Fourier coefficients plus and minus that frequency, the first fundamental frequency. Then we have 5 Fourier series coefficients. That's a couple of sinusoids, and we have this darker gray value, and we see it starts to look like the original signal. Finally, with 11, only 11 coefficients, we are almost there. So the black curve is very close to the original red curve. So we get a precise approximation with only a very limited number of coefficients. And that is good, because now if we needed to just look a little bit beyond 72 hours, we probably could have a pretty good prediction based on this model. But we're not going to go into the prediction. This was just a goal of showing approximation, something we had seen previously when we studied Hilbert spaces. We had looked at Legendre polynomial approximations, for example. Here we have Fourier coefficient-based approximation of a periodic signal. The third example comes back to music, and it's understanding a little bit the magic between MP3 compression. This magic is based on the human hearing system and the clever use of the spectrum, or the discrete Fourier transform. MP3 compressed music sounds pretty good. However, it has been compressed highly from its original format by a factor of 10, 20 or more, and therefore some information has been lost, but the human hearing system has been fooled not to notice this loss. So compression, which will be discussed later in the class, does introduce some noise, some approximation error, and the trick is to shape the noise so that it's not picked out by the human hearing system. We are going to start by simply listening to music and two versions of adding noise. One which is not so clever way to put noise, and the second one is a clever way, which is using MP3. Both noise level are of the same magnitude, so they have the same energy of noise that is being added. So the signal to noise ratio, which is the ratio between the useful signal and the noise, is in both cases 13 dB. So let's start and play the original noiseless music. Now we play the original music plus what we call noise number 1, which is simply white noise and has a 13 dB signal to noise ratio. I guess everybody would agree that this is pretty bad. It's pretty obvious that this is a noisy signal. Now we are going to add exactly the same amount of noise, so SNR is also 13 dB. However, we shape the noise in a clever fashion. And it's probably pretty difficult to distinguish the original from this version, which is the MP3 version. So we have the same amount of noise. There is an impressive difference. Let's understand this secret. And the secret, as you may guess, is found in the Fourier domain. So we plot the DFT spectrum of the music again on a log scale. So that's a top graph, and you see there is some spectral decay, and it has a very particular shape, which depends on this particular piece of music. Then the first noise, which is 13 dB signal to noise ratio noise, has an essentially flat spectrum across all the spectrum. Whereas the second noise, the clever noise, as you can see, has a shape that resembles the shape of the music. And so when the music has a lot of Fourier energy, we can add some noise, whereas the music has very little energy, we put very little noise. So that's called noise shaping. So we summarize this in this graph, where the blue curve is the spectrum of the music, the red curve is the spectrum of the noise, exactly adapted to the music. And the compression algorithm used in MP3 is of course very complex, but one of the key elements is to shape the errors adaptively as the Fourier spectrum changes, because of course music evolves over time, so the Fourier spectrum does not always look like this, it changes all the time. So you have to constantly adapt where you put the noise as the Fourier spectrum of the music changes. And so MP3 magically minimizes the loss of quality by shaping the compression errors in a clever manner, and this is done in something that is called the short time Fourier transform domain, which we don't explain now in detail, but the idea is essentially a DFT that is local. So over small pieces of music, you take a discrete Fourier transform, you look at the spectrum of the music, and you put the noise exactly where it's not going to be heard. This is a magic method, and this is what has made MP3 such a successful music compression algorithm. By the way, this is called perceptual compression, and this is an art because you have to understand not only the mathematics but all the perceptual effects of the human hearing system. And the people that derived the MP3 compression standard, and that's a lot of people are involved in this, have actually brought together all the qualities from mathematical analysis to human perceptual knowledge to derive a very powerful algorithm. By the way, MP3 is not the only audio compression algorithm out there. There are other ones, but all the successful ones will have noise shaping in the same style as what we have just seen for MP3. The fourth example comes from medical imaging, namely a method called magnetic resonance imaging. So MRI is an imaging technique to see the interior of the body. The method in physics vocabulary is that you can excite hydrogen nuclei with a magnetic field, and then you can change the magnetic field, and then the oscillations will be picked out from some sensors outside. We give here a funny picture of a scanner. This is actually not the real scanner, as you may guess, but you can recognize the emblematic red couch from our laboratory. Using digital signal processing vocabulary, what we measure is actually the discrete Fourier transform of the internal structure of interest. So the internal structure is a three-dimensional structure. We may measure, for example, one slice at a time or several slices at a time, depending on how we measure this. And the collected data doesn't look at all like the interior of the body. We can see it here. It's a Fourier transform of the interior of the body. So this is an image, and we see magnitude of Fourier transform coefficients. And so this is the data you're collecting from an MRI machine. Now, the picture we have just seen is not very useful to a doctor in order to investigate what's happening inside the body of a patient. So we need to do something. Well, these are Fourier transform coefficients, so we take an inverse Fourier transform. And then you see, for example, here, the data we had just seen corresponds to a slice of the skull. And you see many details, so MRI is an extremely powerful technique. And by the way, you not only see bones and so on, you see also physiological activities, and this is an incredibly powerful instrument also to do fundamental scientific inquiries. And so that's an example where, because of the physics, you don't have access to the data itself, but you have access to the Fourier transform of the data. So by the setup, you have to take an inverse Fourier transform to recover the data of interest. With this, we're done with these examples. I hope that we gave a sense that the discrete Fourier transform is actually all over the place. We had examples from music, from tides, from medical imaging. We could generate many, many more examples. And that's maybe not the purpose here because we want to understand the tools, but please bear with us. We have many examples coming again and again showing that this is not just mathematics, it's actually very useful mathematics that allows you to do compression, to do imaging, to do prediction, and so on.